discussing in part one, we'll discuss the measurements within our solar system and the Milky Way galaxy. And afterwards, we'll look outside the Milky Way. So, Phil?
Fire this up. Okay, I'll do this underway. Since hardly anybody could come tonight, several people requested I record it. Of course, I didn't have a recorder, so I had to go borrow a recorder today from Rick Honey. So he was, I'll sell copies to people later on. Did anybody neglect to print out the handout? It's
Yeah, I have one extra.
spares, thanks to Freddie.
I printed it, that was on front.
Well, you got part of it.
Anybody else?
You got a second.
Use the print.
Almost half of it.
Use the print. And
The printer I use, it's a community, it prints two of everything. I can't figure out how to get it.
It's better than half of everything.
There you go. That is true.
Good.
That's good.
Okay, this is one I've never done before, so you'll be seeing some slides that are not familiar and not the same old ones. In fact, you can see we got today's date on it, so that guarantees you that it's brand new. This is a chance to review quite a bit of astronomy because all of these measurements are things that determine most of what we know that we cover in the short course and our other meetings. But today we get into the reasons behind all of this and how we know these various things within our solar system and the Milky Way and beyond. If you take a look at the handout, you'll see that there's several layers of direct measurement. We have some that are primary, that are just absolutely direct measurement, like you're using a yardstick or a tape measure. Then other things depend on that, and those are secondary, and still other things depend on the secondary ones, and therefore they're tertiary. We'll notice that as we go through this, we get farther and farther away. The scale of light years down here at the bottom actually winds up with 10 billion light years off in the distance, which is getting pretty close to as far away as anything is. And we start out within the solar system down here at the bottom left. We're not going to go through these in this order because even though this is the order of distance, it's not necessarily the order of how the measurements are made and how one depends on another. So we'll be kind of skipping around on the handout. And one of the things you'll notice is that there's some unnerving gaps in the thing. As we'll refer back to the handout as we go, but you'll see one of the worst ones is there are no Cepheid variables close enough to measure by the parallax method. And that's a major problem in astronomy, is calibrating this, because almost everything from here on up depends on this. And this has got indirect measurements involved in it. So there's a big gap right there. But next month, if any of you come back, we'll have maybe a possible solution for that problem. Okay, the earliest measurements were made by the ancient Greeks well before the time of Christ. Aristarchus made the first astronomical measurements that we know of. They weren't too good, but his logic and his arithmetic and trigonometry were flawless. It's just the data were not very good because of the instrumentation or lack thereof at the time. He figured that he was trying to determine the distances to the moon and sun and the relative sizes of those objects. People had wondered about that a while, and he decided that as long as the sun wasn't an infinite distance away, when the moon was at the first quarter phase and at the last quarter phase, that this angle here would not be 90 degrees, because if the sun were anything closer than an infinite distance, this would be a right angle here and here, but not there and there. So that was his line of reasoning. When he went to try to actually make the measurements, he ran into a problem. The angle is so close to 90 degrees, like 89.999, that there is no way for him to measure an angle that was that small or different from 90 degrees. So then he tried alternate plan B. He correctly reasoned that if the moon were in a circular orbit around the Earth, that the time it took to go from the first quarter around to the last quarter would be a little longer than to go from the last quarter back to the first. And from that, he could figure out the angle that would differ from 90 degrees at the corners of these triangles. And that gave him a little bit better luck to go on. He, of course, making time measurements in those days was tricky too. He didn't have a geek watch that gives you to the nearest second set by WWV. It had water dripping and things like that that they used to keep track of time with. So he had to make years of observations and average them out, because even though his assumption was that the moon was in a circular orbit, he quickly discovered that all his data would be different from one month to the next, because the moon's orbit is not circular, it's elliptical, and it speeds up and slows down accordingly. So he had to take measurements over many, many years and average them out. But when he did, he found that there was about an hour's difference. The distance between first quarter through full around the last quarter, and telling exactly when the moon is at a quarter phase is not just exactly a piece of cake either. You know, it's, you have to have a judgment based on that. Turned out to be about an hour difference in the two halves of the lunar month. And now we know it's an hour, 4 minutes, and 38 seconds. But so that was a pretty good measurement. But still, it was off enough where when he calculated things, it didn't turn out just wonderfully. He measured that the moon's distance was 10 Earth diameters away, and in actual fact it's more like 30. And now this is his closest one. He said that the moon was about a third the diameter of the Earth, when it's more like 27%. And he said the sun's distance was 200 times the Earth's diameter, when it's more like 11,700, so that was way off. And the sun's diameter, he said, was 7 times that of the Earth, but it's really more than 100 times. There are two ways to think about it. These are pretty far off. However, they were the first astronomical measurements made in 200 BC or thereabouts, and he did, all his measurements were in the right direction. The moon is a pretty good distance away compared to the size of the Earth. It's not just floating in the Earth's atmosphere. It's smaller than the Earth, a rather modest fraction of the diameter of the Earth. The sun is much farther away than the moon, and it's quite a bit bigger than the Earth and the moon. So to that extent, he was completely right, just the numbers weren't right on. Eratosthenes lived a little bit later, made one of the first very successful astronomical measurements, and that was the circumference and diameter of the Earth. He noticed that the sun would shine straight down a well on the first day of summer at Syene, where Aswan is now, which is now underwater, I believe. Isn't that right? Didn't they build a dam there that flooded that whole area?
Yes.
Okay, well, so much for the historic well. I guess the well's still there. But in the same day and time, at noon, and that was easy to measure. He could tell when it was noon. He didn't have to have an accurate clock to do that. The sun was 7.2 degrees south of the zenith at Alexandria, which is about 500 miles north of Aswan. Now he, of course, believed, as most intelligent people did then, that the Earth was spherical and the sun was so far away that its rays came at us essentially in parallel bundles. And this was the setup of his experiment. At Syene, the sun would be directly overhead. If you go 500 miles farther north, the sun is no longer directly overhead, but is 7.2 degrees south of the zenith. So he made this following mathematical calculation, that 7.2 degrees there was to the complete circumference of 360 degrees of the Earth, as 500 miles was to the whole circumference of the Earth in miles. And solving for the unknown circumference of the Earth, we come up with 25,000 miles. Divide that by pi to get the diameter of the Earth, and it is remarkably close, probably due to a lot of mistakes canceling out and other fortunate accidents. But this is a heck of a good result for BC.
Well, the difficult thing is at 500 miles.
Right. They use stadia, and we laugh at people today for measuring everything in terms of football fields, but that's kind of what they were doing then.
That's right.
And each one of them had a different value, so we picked the best ones, and it comes out really good.
It does.
So that was one of the first successful astronomical measurements. Finding a better distance to the moon than Aristarchus had, Ptolemy, now we're in the AD era, measuring by parallax. He figured that if you got it two different places on the Earth, you should be able to see the moon against a slightly different background of stars. And of course, everybody's familiar with how parallax works. If you hold your finger in front of your nose and alternately close one eye and the other, it looks like your finger's jumping back and forth against the more distant objects. And he decided to use that method to determine the distance to the moon. If we take, you probably couldn't get 8,000 miles, because then the moon would be on the horizon at both locations. So he knew from Eratosthenes the dimensions of the Earth, so he figured if you got 6,000 miles apart, you could measure this angle, which he did, as 0.7 degrees, and calculate the distance to the moon, and it actually came out pretty close. Now, it turns out that he didn't even have to do two measurements simultaneously 6,000 miles apart. That would have been really difficult to set up an experiment like that. We couldn't do that in the 1800s, trying to measure the transits of Venus and getting the exact times as to when you're taking your measurements. If you just wait a while during the night, the rotation of the Earth takes you from here to here. So the same person can make that measurement from both locations at different times on the same night. And of course, the moon moves some in its orbit then, but Aristarchus and others had carefully worked that out, so they knew how much to subtract off, that the moon was actually moving during that time. So they were able to come up with this angle fairly closely. So here's what I just said already. I forgot I already had another slide on that. So we have to subtract off the moon's distance that is moved during the several hours it takes the Earth to go from here to here. But that's a fairly large distance, isn't it? 7/10 of a degree. The moon's diameter is 1/2 a degree, so this is a considerable distance, and it was fairly easy to measure, not like those thousandths of a degrees that Aristarchus was trying to measure. Okay, Copernicus in 1543 had his famous deathbed book published, De Revolutionibus Orbium Celestium, about the revolutions of the celestial spheres. He calculated the distances of all the planets from the sun in terms of the Earth-Sun distance, known as an astronomical unit. None of these distances were known in actual miles or even stadia, but he was able to put each one in terms of the Earth-Sun distance. And he did this by timing the length of the planet's year and setting up similar triangles as the planets moved, so that compared to the Earth, he could figure out the distance, how much farther each planet was from the sun compared to the Earth. And all of these were measured fairly accurately, And as we'll see from his table here, he was able to come up with almost the same values we use today just from his geometry and trigonometry. For Mercury, he was in Venus, extremely close. Of course, this was by definition, so both of those are going to be 1 no matter what. And Mars was right on, and Jupiter very close. Saturn, a little bit farther off, mainly because it takes Saturn about 29 years to go around the sun, and nobody had ever seen it go around a whole lot of time, so there just probably wasn't enough data that he was using.
How do they get the modern numbers and everything like that, distance and stuff like that? Is that actually from flights and stuff like that to the moon?
Well, if you will hang on for about
Okay.
30 seconds,
Okay.
we'll get to that.
Okay, sorry.
All right, so these are the modern values compared to those of Copernicus. There's an intermediate step, and that is those distances can be polished up quite a bit, because once Kepler had used Tycho's data for the motions of the planets, particularly Mars, he was able to work out his 3 laws of planetary motion, one of which has an exact relationship between the period or the year of the planet and its distance from the sun. And if both of these are put in Earth distances, like this period would be in Earth years, and that distance would be in astronomical units, this is an exact relationship that only needs tweaking a little bit for the most massive planets. So once you know that, then the errors in your data can be kind of ignored, because all you have to do is to measure their year, which is rather easy to do, and then you can calculate the distance directly from that. And here's an example for Mars. Its orbital period is 1.88 Earth years. So if we put that in for the period and solve for the distance, we'll find that it's 1.52 astronomical units. Of course, that's not a real distance, but that's relative, and it's very much correct. So boils down to, with Copernicus's insight and Tycho's measurements and Kepler's equations, it's possible to measure the distance of any planet to the sun in astronomical units as accurately as you can measure its year and its path around the sun. This drawing is originally supposed to reveal Galileo's proof that Venus orbits the sun rather than around the Earth, which was one of the commonly held beliefs then. Here you can see that as Venus orbits the sun, not only does it change its phase, being full over here and a thin crescent over here, but it also changes its apparent size, because here it's much closer to the Earth than it is around on the far side. Now, here is also the experiment that we use to get the actual value of the astronomical unit. And that is that if we know Venus's distance from the sun in astronomical units, and the Earth's, of course, is 1, the difference between those two values is that distance right there, between Venus at its closest and the Earth. Now, Kepler and others had proposed that using a transit of Venus, such as we had this past summer, when the Venus passes directly across the face of the sun, if you could take measurements of the times exactly when Venus touched the edge of the sun and left the other side from widely diverse places on the surface of the Earth, but exactly the same time, you could draw triangles that we could calculate, knowing the distances between those spots on the Earth, to calculate the distance to Venus and therefore the astronomical unit. The first time they tried that, it was clouded out practically everywhere, and the next time around we had other better ways of doing it, so that was never the primary way of measuring the distance. But we still used Venus, so Venus still got to play a part in it, and this was done in 1961 with radar experiments. If you bounce a radar beam off of Venus, it will come back in 138.2 seconds, or excuse me, 276.4. Calculating it one way, we have 138.2 seconds. As accurately as you know the speed of light, multiply it by that time, and you'll see the distance in actual miles. And since that's the 0.277 astronomical units, the difference between the Earth's and Venus's when they're at the closest point, That gives you the distance of the Earth to the Sun is 92.9 million miles. So the radar is the way we know it most accurately. That was a little more than 30 seconds, but
Yeah.
there we are. They've got reflectors on the moon, and we can measure the distance to the moon within inches anytime we want to. If we ever want to just check anything out. Okay, measuring distances to stars by the parallax method. Now, the method that Eratosthenes, but Aristarchus used will not work on the distances to the stars because the baseline of the triangle, the diameter of the Earth, or some fraction thereof, is way too short. This was why the ancient astronomers had ruled out a moving Earth, not because they were stupid or bound to tradition too much, but because they reasoned that if the Earth were moving around the sun, which seemed reasonable to them, once they realized that the sun was bigger and the Earth was smaller, you would expect the little object to move around the big one. The reason they were hesitant to completely endorse that idea is because they correctly assumed that you would see the nearer stars seeming to move back and forth in their positions due to the parallax from the Earth's changing position. And they did. So they kind of ruled out that and went to other more complicated theories. Even with the baseline of the Earth's whole orbit, 2 astronomical units, 186 million miles, no stars are close enough to even give a parallax of 1 second of arc, 1/3600th of a degree. So that's obviously not visible to the naked eye, no matter how sharp-eyed you are. And so no one had ever seen any visible parallax from the stars, which was causing the problem. So we have a 186 million mile baseline, and it allows us to do a little calculation just by triangles. Got some pictures here. If we have nearer stars and then farther stars, and the Earth is going around its orbit with a radius of 1 astronomical unit, we'll see that the nearer stars have a larger parallax than the farther ones. Once again, using your blinking technique, if you put one finger pretty close to your nose, another one out at arm's length, and you switch your eyes back and forth, you'll see that your nearer finger seems to jump back and forth a lot more than the farther one. And the parallax amount is inversely related to the distance. Here's a calculation. If we have a baseline from, say, July to January in the Earth's orbit, it's 186 million miles. And this drawing is obviously not to scale. This looks like about 20 degrees here. For the nearest star, this would be less than 1/3600th of a degree there. So there's no way to draw that to scale because it'd all just be in that line. Okay, suppose you have a star that's at such a distance that its parallax would be exactly 1 second to either side of its center position, its average position. When we look at it from diagonally or diametrically opposite points in the Earth's orbit, we would say that that star is at a distance of 1 parsec. Parsec is a made-up word meaning the parallax of 1 second. So if there were a star at just the right distance, it would have a parallax of 1 second and a distance of 1 parsec. We can see how far away that would be just using standard trigonometry. Here's our angle of 1 second of arc. Here's our opposite side of 93 million miles, the radius of the Earth's orbit. So the tangent is this side over this side. We can solve for the distance to that star, and it turns out to be 19.2 trillion miles. And knowing from previous knowledge that we won't go into tonight, that a light year is 3.2, our parsec is 3.261 light years, we can see that 19.2 trillion miles, or 1 parsec, is equal to about 3 1/4 light years. Keep in mind, from your previous knowledge, that Alpha Centauri, the nearest star system to us, is about 4.3 light years away. So there aren't any stars close enough to even have a parallax of 1 second. They're all less than that. So measurements are a tricky thing to do. Sirius, here's an example of calculating the distance to the star Sirius, the dog star, the brightest star in the sky, still visible out in the southwest. It has an annual parallax of 0.77 seconds, so we know it's farther away than 4 light years, right, because it's less than 1 second. And the radius, half that distance based on the 93 million miles is half of that, 0.385 seconds. The easy way to do this is the way the definition of a parsec is set up. The distance is just the reciprocal of the parallax. So 1 over 0.385 is 2.60 parsecs, and there's our conversion factor. It tells us that Sirius is 8.5 light years away. Doing it by direct trigonometry, we'll see that the tangent of that angle, 0.385, is the opposite side of the Earth-Sun distance over the distance to the star, and then solving for x just by trigonometry, we come up with 49 trillion miles, which works out to be 8.5 light years, or 2.60 parsecs, same as we had before. So you can just, the easy way is just taking the reciprocal of the distance in parsecs, or the parallax in parsecs, and that gives us the distance. So those are how we measure this for relatively nearby stars. Bessel actually used visual observations, but you can see how this is going to be a problem. When you look at the star field in January and you look at it in July, so well, the way I remember it, back in January, that star was right here and now it's over here. That just doesn't quite cut it when we're measuring these angles less than a second. So we had to kind of wait for the invention of photography to come along in about 1850, 60, 70, before any sort of accurate parallax measurements could be made. Then you could compare the photographic plates with careful machines. I've seen some of those original ones in the Allegheny Observatory at Pittsburgh, where they would take these photographic plates and put them in there, and with wires moving back and forth, a filer, micrometer, they could measure these distances down to a very small fraction of a second and get the parallax measurements of the distances of the stars with about 20% accuracy. But shoot, that's good compared to what we had before that, which was pretty much nothing. Computer measurement of the photographic plates, and then the CCD detector elements, and then with the Hubble telescope above the Earth's atmosphere to rule out all the shimmering and sizzling that goes on when you're trying to take a photograph of the sky. That extended the reach of the parallax measurements up to several hundred, 500 or 600 light years of fairly accurate measurements. Okay, other methods of measuring this. On your handout, by the way, if you're keeping up, we just did the bottom two, the radar and the heliocentric parallax. We're now into main sequence fitting, which is sometimes called spectroscopic parallax. This is one of those misnomers that is caught on, so we have to address it. It has nothing to do with parallax, except that you use parallax to measure distances to stars, right? This measures distances to stars, so you can call it parallax, even though it's not. It's sort of like if you have two copper tubes, one that fits tightly inside the other, you say they're telescoping, even though it has nothing to do with making distant objects look closer. That's just the way words evolve. So let's call it main sequence fitting rather than spectroscopic parallax, but you will run into that term. This all based around the Hertzsprung-Russell Diagram, and that's one of the cornerstones of 20th century astronomy, and we'll take a look at those in just a moment. If we measure the spectral class, which is essentially the color or temperature of the star, and if we happen to know how far away, or we happen to know how bright the star appears in the sky, we can come up with a pretty good estimate of its distance from that. Let's just see how that's done. There's Hertzsprung and Russell. He was Danish. He was at Princeton. And I've shown them looking away from each other because they did not work together. They independently came up with this. notice how ancient all of this is. They were both still alive when I joined the Astronomical Society, so these are relatively new guys.
They met several times afterwards.
After, yeah.
Yeah.
But it was about 1910 or so that
Yeah.
they were doing most
Yeah.
of the work. And, I'll say about 1910, they tried to see if there was some correlation between the true brightness, absolute magnitude, or luminosity of stars. By then, distance measurements had been made on enough nearby stars that we knew how bright they really were. Because when you look at a star in the sky, it's certain brightness. Well, that's due to two things: how bright it really is and how far away it is. That had been sorted out by 1910 for all of the nearest stars. And so they made a graph. Scientists want to see if there's any kind of correlation between one variable and another. You make a graph with those as the coordinates. And they plotted the spectral type, the "Oh, be a fine girl, kiss me" along the x-axis, and which is decreasing temperature. It's a bass-ackwards graph in both directions. The high value of the temperature is on the left, near the origin, rather than across the right, as you'd expect. And even though the absolute magnitude scale looks like it's increasing, remember the magnitudes are backwards. The sixth magnitude is fainter than first, so it's backwards too. So they found that when they did this, most of the stars on the diagram seemed to follow a pattern from upper left down to lower right. And there were some other concentrations at other spots, and we really are just about to see one of these. There's one. Here's the Hertzsprung-Russell Diagram. It's kind of sparse of stars in the middle. They should have shown a few more on here because they've got just about as many exceptions as they have those that follow the rule. But a very high percentage, more than 90% of stars will be somewhere on this band from upper left down to lower right. And they, of course, felt that that was a significant observation, which it is. And they also saw that there were some exceptions, some things up here, things down here, even a few across the top of the middle. And those exceptions are extremely important as well, as we'll see when we're getting into some of the more remote distance measurement techniques. They call this band the main sequence because of a mistake. Everybody does their work and improves on what was done before till they get up to the point where they screw up. And then they get kind of a dead end, and then the next ones come along and fix that and run into another dead end farther along. So their problem was thinking that stars started out up here and gradually evolved to get down to here, from blue giant brilliant stars here at the beginning down to red dwarfs there. So they call that the main sequence, and again, we still call it that even though there is no sequence. In fact, we even call these spectral subdivisions. If this was, say, G0, G1, 2, 3, 4, 5, we'd call one here an early G star and here a late G star because of the thought that it moves, the stars go along this graph in that direction, even though that's not true.
Okay, I'm looking at this graph and everything, and I see the line that goes through, and I'm assuming everything that's in the line, that all those stars fit their hypothesis, and all the stars that are outside of the line don't fit their hypothesis. Is that correct so far, that statement?
Well, they didn't have a good explanation for how these were here, those were there, if they all started here and wound up there. That's what you mean, yes.
Right. Now, is there, as far as the ones, I mean, some of them are on one side, some of them are on the other side. Does that mean that the ones on the bottom side were off?
Too dim.
Too dim?
Right.
And the ones on the other side were brighter than they thought they were supposed to be?
Yes.
Okay.
Since you brought it up, I wasn't going to go into this tonight, but okay, stars down here are the red dwarfs. They're the ones that just barely enough material there to be a star. These up here are at the same temperature, but they're a whole lot brighter. What's the only reason that can explain why a star that is the same surface temperature as this is 10,000 or 100 million times brighter? That's because its surface area is so much larger. And those are the supergiants there. What about a star like Sirius, which is in here? What about a star that has the same surface temperature that's only a tiny fraction as bright? It just must be a whole lot smaller. So those are the white dwarfs down here.
Okay. One more question.
Mhm.
Okay. You said that there was like about half of the stars that are in the little group in the line that are the way they think they're supposed to be, and then about half of them outside.
No, it's more than that. It's
Oh,
more
it's-
like 90%.
Oh, 90% in there.
Right.
Okay, okay.
Yeah. Yeah, this diagram is kind of skewed because it looks like just about as many exceptions
Okay,
as are on
okay.
there. But picture this, if you will, just all filled in with stars from top to bottom.
Okay.
Also picture some white ones because they've colored them blue for some reason.
Okay.
The majority of stars in the lower right, correct? In the universe.
Right, yes. Which is why we don't see most of them. Yeah, yeah. If you look throughout the sky, there are only one or two red dwarfs that you'll actually see, even in a telescope, because they're so inherently non-luminous that they just don't put out. Okay, here's an extremely important thing, Wien's displacement law. Wilhelm Wien was a physicist and an astronomer, and he noticed that in a laboratory, when you took the spectrum of a glowing wire, like a tungsten light bulb filament, and you turned up the voltage and it got hotter and hotter and brighter, some interesting things would happen. No matter where he would have the voltage set, there would always be a rainbow spectrum produced by a solid surface like a light bulb or the surface of a star, for that matter. And the higher the voltage was set and the brighter it got, in those cases, the amount of light put out was always greater at the higher settings. He also noticed that if you measured the intensity of the spectrum, it was not uniform from one side to another. Even Newton started out doing some experiments with this with a crude thermometer along a spectrum, and noticed that you get different temperatures and different colors depending on what you're looking at. The sun, for example, puts out its maximum energy in the green part of the spectrum, around 500 nanometers, 5,000 angstroms. It doesn't really look green here, but it is green. Does anybody know where the maximum sensitivity of our retina is?
Yellow, I think.
It's in the green. It's right at that same spot.
Penny's old.
They're just very close. It's amazing how the sun has evolved in order to exactly match the sensitivity of our eyes, which is the way you have to put it in this part of the country. So, anyway, suppose we have a cooler star like Antares. It has a rainbow spectrum as well, but its peak is in the red or even in the infrared. And if you have an extremely hot star like Rigel, its peak is at a shorter wavelength. In other words, the hotter the star, the shorter the wavelength where it has its peak emission. Okay, is everybody clear on that? Crank up the voltage, get it hotter, it puts out more energy everywhere, but the peak moves to a shorter wavelength. This is one of those things where, man, this is a eureka moment to have discovered this. Wien discovered that if you take that maximum wavelength and multiply it by the temperature, you always get the same number, the constant. That means that all you have to do to measure the temperature of a star is to take the spectrum of it, see where its maximum wavelength is, and put that into this equation and solve for the temperature. If we do that for the sun, its maximum wavelength is 500 nanometers in the green. If you put that in for here, you'll find that its surface temperature is 5,800 Kelvin or 5,500 C. So there's one more beyond the one more. Okay?
Question. As far as when they were doing the testing and everything like that with the wire and getting the temperatures and stuff like that, any idea what type of temperatures they were using? I mean, the only reason I'm asking is
These, and you could measure those with a thermocouple. They tend to call it a bolometer in some of those early experiments, but that was developed enough then to actually measure temperatures with thermal emissions of dissimilar metals.
Okay.
So You could do that with the wires in the lab, of course, not with the star. You had to assume that the same rules applied. Once you've got the equation worked out, then it would apply to anything.
And that was going to be my next question is, I mean, I can take like a glass of water and I can put it at like a small fraction of temperatures and I can make determinations on how that water is going to act at that small determination of temperatures. But from that small window that I'm using, I can't really necessarily say that the water's going to freeze, the water's going to boil.
No, it's all different stuff.
Right, true.
Yes.
But what I'm asking is, I'm assuming that the temperatures that they used weren't anywhere close to the temperature of the sun or other stars and stuff like that, or
Yeah.
they were?
Yeah, the
Okay.
filament in an ordinary light bulb is hotter than Antares.
Okay.
Yeah. These all apply to incandescent substances, things that glow because they're hot.
Okay.
And water generally doesn't do that.
Right.
You get into the infrared, you can measure emission from anything. A glass of water at room temperature will show up with an infrared sensor, but this was all in the visible part of the spectrum that they did that work. Okay, so here's how we determine the distance to a star using the main sequence fitting, aka spectroscopic parallax. You take the spectrum of the star, measure its maximum wavelength, and you calculate the temperature using Wien's law. The example I picked here is one that's at about 7,500 degrees Kelvin on its surface temperature. Then we read down to the main sequence and over to the y-axis that tells us its absolute magnitude is 2.5. If it's one of these stars here, not one of these and not one of those, but there are other ways to tell, which we can't possibly go into tonight, but we can tell if a star is a main sequence star or not. And so measure the temperature, find where that is on the x-axis, read off as though this were a calculated line on a graph, read off to the side, and that tells us the absolute magnitude of that star. Then, using the inverse square law, which says that the difference between how bright it really is, the absolute magnitude, and how bright it appears, the visual magnitude, is just a function of how far away it is compared to a standard distance of 10 parsecs, and this makes the numbers come out right. So, and then that's squared because, twice as far away gives you 1/4 the light and so on. So if we, suppose we measure that same star we were looking at on the previous slide, and its visual magnitude is 9.48. Okay, and we previously saw that its absolute magnitude off of the graph was 2.50. Well, we put those values in here, calculate the only unknown left, and that's the distance. We see that that star is about 800 light years away. So that's how you actually do the calculations to do the main sequence fitting or spectroscopic parallax. Okay, here's a neat one. Supernova remnant expansion. The only bad thing about this is that they're kind of few and far between, and they're not common enough to be extremely useful, but when they are there, they verify some of our other measurements and make us feel good about what else we're doing when we don't have this method to back it up. When a star explodes as a supernova, it sends out a shell of wreckage that keeps expanding kind of rapidly, hundreds of miles per second, but nowhere near the speed of light. And if we look near the center of a supernova remnant, we have to assume that the material there is coming straight towards us, whereas the stuff near the edges is spreading out in either direction. First, a little bit about the Doppler effect, because that's the technique that we use. Everybody knows about the Doppler effect for sounds. You always hear about a train coming towards you as it's approaching, the sound of the horn gets higher, as it passes, it drops down. My favorite is if you watch kids flying model airplanes, if they're on a tether and they're just going around in a circle, you can hear the pitch of the engine going up and then down and then up and down as it's coming towards you and going away from you. You assume the engine is, the kid in the middle thinks the engine's got a constant sound, but if you're off to the side, you hear it rising and falling. because when the source is moving towards you, the sound waves get bunched together and they hit your eardrum faster and give you the sensation of a higher pitch. And when it's going away from you, the waves are stretched out and they don't hit your ear as fast, and you get the sensation of a lower pitch sound. It works the same way for light waves. Suppose we've got a star that's stationary, and suppose it's a yellow star. When we see it, it's not moving towards us or away from us, so it looks yellow to us. Suppose that star is rushing towards us at a pretty high speed. Its waves get bunched closer together, and therefore, when our eye sees it, it can't tell whether it's a yellow star bunching its waves up or a blue star just sitting there. If it looks blue, it looks blue. So even though it was yellow to start with. And by the same token, in the opposite direction, if a star is receding rapidly from us, its wavelengths get stretched out and it looks just like red light to us. So you've heard of red shifting and blue shifting. That's because of objects moving towards us or away from us, bunching up or stretching out their waves so that they give us the same impression as if there were those wavelengths when it was emitted from the source. Okay, so if a star or galaxy is approaching or receding, its light waves are whatever color they're emitted, and I keep picking on yellow here because it is in the middle of the spectrum, and because sodium has a couple of dark lines right in a very convenient place that are easy to measure and they're easy to pick out of a spectrum, so we can tell whether they're where they're supposed to be or whether they're too short or too long, whether the source is moving or not. And all the other wavelengths move around as well, but that's an easy one to pick out.
You said too short or too long?
Right, yeah, compared to what it would be in the laboratory. If you have a sodium vapor lamp sitting in the laboratory and you have a prism and a table with a protractor on it, you can measure exactly the wavelength of that, where that dark line is. Now, if that light were coming towards you, you know, if you measured that it was several nanometers too short from where the book said it would be, you better get out of the way because that means it's coming at you at an appreciable fraction of the speed of light. Okay, here's one of the simplest equations in all of physics and astronomy that's one of the most important. When something's moving towards us or away from us and its light is shifted by a little bit, if we compare that shift in the wavelength to what it's supposed to be when it's sitting still in the lab, that's exactly the same ratio as its speed to the speed of light. Now that's profound and simple and exceedingly useful. So if we solve this equation for V, we'll just see that's the shift, either red or blue, compared to its laboratory standard times the speed of light. That gives us the actual speed of that object. Now, this equation only works when we're dealing with speeds well below the speed of light. There's a more complicated version, which we'll see right near the end, when we're out at the fringes of the universe and things are moving at an appreciable fraction of the speed of light. But for most ordinary objects, this equation works just fine. Okay, here's an example. Suppose we have a star who's, suppose we have a normal wavelength of 2,000 angstroms, 200 nanometers, and it's showing up about 2,500. Okay, that's lengthened, so it's receding from us. 3,000 going to 3,700, that's still receding. We measure each one of those little shifts across here and divide it by where it's supposed to be. We take each one of those little shifts divided by the stationary number, and we'll get the same all the way across because they're all shifted by the same percentage. In this case, 0.2. So that tells us that this object is receding from us at about 20% the speed of light. So it's a straightforward measurement and an even simpler calculation. Now, another sidebar here. We don't want to go into all of stellar evolution tonight. That's a day-long thing itself. And Rick's recorder, he said, holds 17 hours, and he's sure I could fill it up. We don't want to do that tonight. Let's just look at this upper curve here. This main sequence, which isn't a sequence at all, Up at this corner of it is where the blue giants are. Blue giants like Rigel eventually turn into red supergiants like Betelgeuse or Antares, and then instead of dying out gracefully, they tend to undergo massive explosions known as a supernova. And we'll see what that results in. Here's a red supergiant like Antares or Betelgeuse. In each of these little concentric onion running like circles in there shows different elements being made. And once it gets to where it's making elements heavier than iron, the center of that star no longer produces energy and heat, it uses it up. And instead of supporting itself against the force of gravity, which is trying to collapse it, now it's sucking energy out of itself, and gravity and coolness in the center are working in the same direction. So in the space of a few hours, the star collapses on itself, falling into the middle. There's a bounce and a rebound, and then an explosion occurs there, and the shock wave goes back out through the outer parts and forms heavy elements in all of this outer part of the star, which eventually get recycled and turned into solid planets and people and stuff like that. That's another whole story. But we're looking at this wreckage expanding throughout the sky. One of the most well-documented of these was the supernova of the year 1054, when Chinese astronomers noticed what they called a guest star in the constellation Taurus. They had a different name for it, of course. It was so bright it could be seen in broad daylight for a couple of weeks. And they carefully recorded its position. Now, this was centuries before telescopes, but later on, after the telescope was invented, we looked back at that same place they had documented in the sky, and this is what's there now. This is what we call the Crab Nebula in Taurus, and the star that did it all is that little one right there. It's spinning around very rapidly. It's a neutron star, also a pulsar, and it's still expanding. The measurements that have been made on it show that if you calculate the rate of expansion and then extrapolate it back to where it started, it comes reasonably close to the 1054. We're certain from the time and the position that that's what it was. Until one of the Magellanic Cloud in 1987, this was the most well-studied supernova remnant. Okay, it's now 4 by 6 minutes in diameter. This is an exercise, by the way, in how to measure the distance to the Crab Nebula, and we can do it almost directly. In fact, our sheet, we're the third one from the top, supernova shell expansion, that says primary. We've got a primary distance measurement there, and the only trouble is they're kind of rare. So it's got to be expanding at the rate of 3 minutes every 950 years, since that's when it happened. Okay, the D line of sodium that I mentioned before has a laboratory value of 589 nanometers. It's blue shifted because when we're looking right at the center, that's coming towards us. That shock wave and the expansion is moving towards us, and it's blue shifted by a slight amount, down to 586.76 nanometers, or 2.24. That's a small amount, but they can measure that. So using the equation we had before, that shift divided by the rest wavelength is equal to the velocity divided by the speed of light. So we see that the velocity of that material coming towards us in the middle is about 0.3 or 0.4% of the speed of light. It's rather slow, about 700 miles per second that material is moving towards us. Okay, here's where the payoff comes in. 707 miles per second. This is the number of seconds in a year, which is easy enough to calculate. And it's been going for 950 years. And this is the distance of a light year, 5.88 times 10 to the 12 miles per light year. This tells us that that radius is 3.60 light years. So that's a direct measurement of how we know how fast it's going, and we see how far it's going in the sky. That distance is 3.60 light years. Now we set up a triangle. The angle is 3 minutes from the center out to the edge. This side of the triangle is 3.60 light years. What's the distance between us and the Crab Nebula? Stalls right out at 4,100 light years is what the textbooks say about the distance to the Crab Nebula.
Question, okay, the blue shift is, I'm kind of not really positive what that is exactly. I mean, is that a shift from a yellow light to a blue light? I mean, is
No,
there
it's
like
more
a,
blue. It only shifted 2 nanometers.
right, but I mean, is it
It's
get,
not gonna look blue, it's gonna look yellow, but with a little shorter wavelength compared
okay,
to where it's
and that's what I was gonna ask. I mean, do they measuring that through the wavelength?
Yes.
Or,
Yes.
okay, I got you, okay.
Whoops. Yeah. That's the
And the-
wavelength that you measure on this material coming right at you. Here's what it is in the lab. That means that it shifted that much, which means it's coming right at us at that speed.
Now, is the wavelength measured through the shift in color, or is the color measured through the shift?
Position on a spectrum, a photographic plate,
Okay,
they're both going to look yellow. You know,
Right,
if you shift
right.
it by that much, it's still in the yellow, but it's shifted towards the blue end of the spectrum. When you say something's blue shifted or red shifted, that doesn't mean it's blue or
Right,
red. It's
right.
just gone that
it's
direction.
moving in that
Right.
direction.
Mhm.
Okay,
Okay.
okay, I got you.
Okay. Okay, the second half is shorter than the first half. It's more like 2/3 and 1/3. So take a quick break here and we will resume with things outside the Milky Way galaxy for the most part. Okay. Okay, Cepheid variables. So we're kind of skipping around on here, but we're about the 5th thing from the bottom on the handout. We'll take a look again at the HR diagram and see where they are on it and their significance in stellar evolution. Someday the sun will probably be a Cepheid variable after it's been a red giant and sent out a planetary nebula. It goes through an irregular period of its life where it fluctuates in brightness and color, and then eventually kind of simmers down, becomes a white dwarf. Now here's another Hertzsprung-Russell diagram, and sun's position right about in here, and here are the red dwarfs down here, and the blue giants up here. When the sun, or any solar type star, runs out of usable hydrogen, it goes up here and becomes a red giant, and sends out a shell of gases around it like the Ring Nebula. And then as it gradually gets hotter and hotter, as it shrinks down, it goes through this period of instability, and over a period of hours or days fluctuates between a couple of different spectral classes and changes in brightness as well. So that's where the Cepheid variables are on the HR diagram. And then eventually they settle down and come down here and become the white dwarfs like the companion to Sirius. So the most important thing about that is they do vary, and they're easy to find, and they're among the brightest intrinsically of all the stars. If red dwarfs could be used to measure distances, that's too bad because you really can't see them at any great distances. But these are right up at the top of the HR diagram, and they're among the most luminous of all the stars. Here's another version of that. We've got like the upper left corner of an HR diagram with the sun right here now, and red dwarfs are way on down. And the sun eventually becomes a red giant here, sends out a planetary nebula, and then becomes unstable. The crosshairs where the Cepheid variables are located. And then it becomes the central star of the planetary nebula. I don't know why they didn't give us just another inch or so on the diagram, but it doesn't discontinue. It comes back here and then becomes a white dwarf down there. So that's the quick version of the life cycle of a star that becomes a Cepheid variable. Their periods vary from a few hours to around 100 days. And it has an asymmetrical light curve that increases faster and then tapers off. We can estimate the distance to some of the nearer ones. They're not really within the range of parallax. If you notice, see on the diagram, the Cepheid variables, the nearest ones are more than 1,000 light years away, and the heliocentric parallax is only good to a few hundred light years, extended almost up to 1,000 by stretching things with the Hubble. So there's a gap there between any direct parallax measurement of the Cepheid variable. As I said, I'll talk about that next time.
Let me make one comment.
Yeah.
I studied that a little bit, and Harlow Shapley was the one who did it.
Right.
Either he made a guess or he cheated. I don't know what because he doesn't explain it.
That's the way some of these people are. I had an advisor in graduate school that he was a miserable teacher. He was brilliant, but he didn't go through steps. He couldn't explain what he did. He just went from A to Z and was mystified that everybody couldn't do that. And it wasn't cheating. I mean, he just did it. He didn't go through steps. So a better way is to find the star cluster that has a Cepheid variable in it, and by fitting the star cluster's information onto a Hertzsprung-Russell diagram, then we know that if all the yellow solar type stars are where the sun is, and the blue giants are up here, and the red dwarfs are down there, then these ones up here at the top, if they're part of that same cluster, they've got to actually be that bright. So that's the assumptions. And then if we can measure their visual magnitude, then we can get their distances. Here's what the light curve of a Cepheid variable looks like. A quick rise and a longer tapering off as the size fluctuates. It doesn't really show the color fluctuating, but it goes from kind of a pale yellow to a deeper yellow as it goes back and forth from one to the other. And I'm not going to go into the mechanism of that tonight. That's a complicated subject which we can do some other time. Yes?
Can you go back to the first Cepheid variables slide? I have one question. It had like the types, like the O, B, A, F, G.
Yep.
What is that exactly?
That's the spectral classification. These are the bluer ones over here and the redder ones over here. And these all stood for something long ago, but
So that's just the color spectrum more or less?
Yes.
Okay,
Yeah.
okay, I got you.
This is like, it's like Roy G. Biv going this way.
And this is the color spectrum between red and blue?
Red and violet over here.
Red and violet, okay. And F would be?
Yellow, white.
Oh, white,
Okay,
okay.
G is the sun, yellow, and A is Sirius up here. All of these that have names along there, you know what they look like, and that's an example
Okay.
of each of the types.
All right, thank you.
Okay. Now, it turns out that when you measure the period of the Cepheid variable, which is like from here to here, or there to there, it's related to its actual luminosity. And once you determine that, then you can see there's a nice shortcut here. You don't have to measure the distance to it anymore. All you have to do is see how long it takes in the bright and dark cycles and measure the period, and then read off of your graph and see how luminous it really is. And then how it compares to that in the visual magnitude. We can use our inverse square equation again and calculate the distance. Here's the diagram that shows now this is a log-log plot. The period here, you can see it's logarithmically arranged, and so is the luminosity. Even though luminosity itself is linear, the way it's plotted, we can see it's logarithm in that direction. And we get almost a straight line with some scatter. You know, the main reason for that scatter is measuring the distances to them. We don't really know their true luminosities because we don't know their true distances because we can't get any of them really by parallax. Major problem. And also it turns out there are two different graphs, one for the population 1 stars that are in the spiral arms of a galaxy, and the other for the population 2, which is the ones near the nucleus or in the globular clusters around the nucleus. And that wasn't known for a while, and we'll see in a moment how that threw off all the distance measurements for a good while. Henrietta Leavitt, back in 1911, did a lot of the spectroscopic analysis and classifications, and she was one of the first ones to use that system of the ODAFG business. I probably should have looked up what the letters actually stood for, but it's not "Oh, be a fine girl," but anyway, it's that's the way we remember it now. She used the Cepheid variables in the smaller Magellanic Cloud to determine the relationship between their luminosities and the periods. The only problem is those were type 2 Cepheids, and she didn't realize there were two different kinds at the time. When Harlow Shapley measured the distances to Cepheids in the globular clusters, he at first came up with a size of the Milky Way that was about half what we think it is today, because his logic was flawless, just like Aristarchus. He figured that if all the globular clusters were in a swarm surrounding the nucleus of the Milky Way, and he measured the average distance to each one, right at the center of that should be where the center of the galaxy is. And that's what he did. Later on, that had to be corrected. I've already got the corrected figure here, that we're about 33,000 light years from the center, but he originally had it more like 17,000. Edwin Hubble pursued that work farther and started measuring Cepheid variables in the Andromeda galaxy, which a lot of people still called the Andromeda Spiral Nebula back then. There was a big debate on whether these little spiral nebulae were gas clouds within the Milky Way or whether there were actually other galaxies. And this pretty well wrapped it up. When he measured the distance to Cepheids using the biggest telescope in the world at the time, he found that the Andromeda Spiral Nebula was 1 million light years away, which if Shapley had just come up with the idea of 50,000 light years for the size of the Milky Way, this clearly put it way outside of our galaxy. Then, in 1952, when they finally realized there were two different populations of Cepheid variables, each one with its own calibration curve, then the size of the universe and everything in it doubled overnight, and now say that the Andromeda galaxy is 2.5 million light years away instead of just over 1 million. So that literally happened overnight when they made that correction. They just went through and changed all the distances to everything. Here's another kind of star that's similar to a Cepheid variable. They're also very luminous. They're unstable stars that are solar type near the upper part of the center of the Hertzsprung-Russell Diagram. On their way out, they've been red giants, and they're on their way to being white dwarfs. They have a very distinctive light curve and are easily recognized. They're kind of like Cepheids. You see, they gradually taper off and then rise suddenly, gradually taper off. But notice that at the bottom of the curve is a little blip. It goes down, blip, and then back up, and then gradually down, blip, and then back up. So that extra blip identifies it as an RR Lyrae variable. Now, these are several. Notice they all have the same period. And most of them do. And even more fortuitously, all of them have the same absolute magnitude. So we don't need a period luminosity curve like we do for the Cepheid variables. All you've got to do is find one, and you know that its absolute magnitude is 0.6. Not quite as bright as the Cepheids, but there's no ambiguity as to how bright it actually is. And fortunately, both of those types are near the upper part of the HR diagram, so if you're going to find any individual stars in some other galaxy, it's probably going to be these, because they're among the brightest ones. So if you focus in on one of those and it's got that characteristic variable light curve to it, then you've got a yardstick to measure the distance to the Cepheid, because once you know its luminosity and how bright it actually appears in the photograph, the visual magnitude, then we use our inverse square equation again to calculate the distance. Here's some things that I've never talked about to you all before. Some other methods of measuring distances. Planetary nebulae have a spectral line at 500.7 nanometers due to forbidden transition in oxygen. Forbidden doesn't mean it doesn't happen. It's just like if you forbid your kids to come in after midnight, that just means they have to sneak in. So the 500 nanometer line in oxygen is one that does take place. And there's an interesting thing about this. Whenever you have a planetary nebula, the oxygen line there, oxygen 3, always has the same brightness, no matter what. No matter how much oxygen is there or anything else, because there's an interesting feedback mechanism. Oxygen, in the presence of a planetary nebula, tends to cool it down. And the cooler it is, the dimmer that line would be. But the more oxygen is there, of course, there are more atoms emitting the light, so the brighter you would expect it to be. Those two effects exactly cancel out. If you get more oxygen, it should get brighter, except that cools it down and makes it dimmer. If you have less oxygen, that should make it dimmer because there's not as much there, but that lets the temperature go up and that makes it brighter. So that line is always the same brightness. So if you can find a planetary nebula, you can measure the distance to it just from the oxygen line compared to standards. That's especially useful in globular clusters because there are a lot of them there. They're out of the plane of the galaxy. They're not part of a cluster that has a well-defined HR diagram. There's no good way to do it. And elliptical galaxies are mainly made up of globular clusters, so it's especially good for finding them.
Why is it called an oxygen 3? I mean, is there like line? I mean, was there like an oxygen 1 line? And then
yes, it's oxygen that's lost 2 electrons. Now, astronomers use a different mechanism of labeling these things. Chemists would call, say, a neutral hydrogen atom just hydrogen. Hydrogen plus 1, where it's lost the electron. Astronomers call neutral hydrogen hydrogen 1, and the hydrogen plus is hydrogen 2. So hydrogen 3 means it's lost 2 electrons from the normal state of oxygen 1, which is neutral.
Okay.
I wasn't going to go into that because if you do understand it in chemistry, then you don't in astronomy because it's
Okay.
a whole different system.
When does it state correctly for?
Oh yeah, well, you know, if there's a shell around it, you've got to allow for the fact that the light is partly coming through its own spherical shell, like the Ring Nebula. So it's going to be partly dimmed by the outer parts of that, and there are ways to figure that out. You look at the thickness of it off to the side and assume that the light coming towards you through the center is going through the same thickness, and you subtract off the, or you make a correction for the amount of light it's absorbing from itself.
Oh.
So it's, again, it's a lengthy procedure, but it's straightforward. You just have to correct for the fact that it's going through layers of gas to get to you. Okay, here's another one that we haven't looked at, and that's the average brightness of galaxies assumption. The assumption here is made, and it's a big assumption, that if you have a cluster of galaxies and you have another cluster of galaxies, not all the galaxies are the same brightness, but if you have a diversity of different types of galaxies in each cluster, then the average brightness is probably going to be the same from one to the other. Now, you tell me how accurate that's going to be, but sometimes that's all you've got to go by. And if you see one cluster that's dim and another cluster that's bright, the logical assumption is the dim one is farther away. And that's the average cluster of galaxies. And that you only use that when nothing else works. You can't find any Cepheids or RR Lyrae stars. It's just barely there itself, much less any individual stars to go by. So that's kind of a last gasp thing. It's not particularly accurate. However, for a long time, that was the best we had on some measurements. The Virgo cluster of galaxies, the average brightness leads to estimate that it's 16.5 times farther away than M31, so make that about 38 billion light years. So that gives you a ballpark figure, and sometimes that's better than what you had. Here's another one, galaxy pixel fluctuation. This is a more modern method that's come into being after CCD imaging became prominent. The idea is that there are a lot more stars in a galaxy than there are pixels in a CCD array. I think we'd all agree with that. That means there are many, many stars in each pixel. Now, if you look at this statistically, and there are lots and lots and lots, zillions, trillions, bazillions of stars in each pixel, there's more likely a chance that each pixel will be just as bright as the neighbors around it. However, if the stars are sparsely distributed, and there are only, like, say, 5 stars on each pixel, that's an extreme case, then these 5 and these 5 and these 5 could well be different. So there'll be a lot of difference in brightness from one pixel to the next. So the uniformity of the brightness of the pixels is directly related to the crowding of the stars in the image and how many stars that galaxy has, and therefore how bright it is intrinsically. Well, then compare that again to how bright it looks on the photograph, and we can kind of come up with an estimate of the distance. Again, this is not by any means a primary method, but it does work, and in some cases it's verified by other measurements that are better. So when we have nothing better to go on, this way works pretty well, actually. Here's another one that I haven't mentioned before, the Tully-Fisher method. And it's fairly new. At least to me, that's fairly new. That's 20 years after I started coming to this group, so this is brand new. Here are the two assumptions. The more massive a spiral galaxy is, the faster it would rotate, because the mass in the center that the stars are orbiting around makes them move faster. And the more massive spiral galaxies have more stars in them, so they'd be more luminous. So if this is related to that, and this is related to that, then this should be related to this. That is, the faster they rotate, the more luminous they should be. So if we measure the rotation speed by the Doppler shift, in other words, we don't have to sit there and watch a galaxy make a turn and time it, because, you know, where we are in the Milky Way, it takes 100 million years to go around. We wouldn't have very much data that way. But if you look at the Doppler shift near the edges, one side's coming towards you, the other side's going away from you, you can see how fast it's rotating. And we normally use the broadening of the spectral line, like the 21 centimeter hydrogen line. You know, if you go from one side of the galaxy to the other, part of it's coming towards you, part of it's sitting still, part of it's going away from you. So that makes the line red shifted and blue shifted at the same time. So it's just broadened. The line is broadened. So you look to see how much the line is broadened, and that tells you how rapidly it's rotating. And then we use this formula, which I'm not going to derive tonight here, but this is the intrinsic absolute magnitude. The W stands for the width of the line, how much it's broadened, and these are all empirical numbers, fudge factors that give you plus or minus a tenth on the magnitude there. They're pretty proud of it. I don't think I would be that reliant on that. But if you, that gives you the absolute magnitude of the galaxy based on the, and this is for spiral galaxies, based on the width of the spectral lines due to the fact that it's rotating. The faster it rotates, the more luminous it is. And then, of course, the last line of all of these is the same. You compare it to the visual magnitude with the inverse square equation and come up with the distance. You can see this actually works out pretty well, you know, despite the fact that it is a log scale. This one says log and this one doesn't, but the magnitudes are logs anyway. You've got kind of a lot of scatter there, but it's certainly better than what say social scientists come up with and claim they have a relationship. So this is definitely a good relationship there in the two variables.
What is the size of, I mean, I saw the circles were on that line, and I mean, some of the circles are smaller than others. Does that mean?
Yeah, that's some error bars. They, instead of putting in error bars, they made the size of the circle different to indicate the slop in the measurement.
Okay, okay.
And if there were tiny points, you'd say this one was really there, but it could be here, there.
Oh, okay, I got you.
Here's a similar method, same line of reasoning, And that is, again, more massive elliptical galaxies have a greater dispersion of stellar velocities near the center. In other words, they probably all have mega black holes at the center, and the globular clusters near the middle are rotating around it. And the more massive that black hole is, the more luminous the galaxy is, and the faster things rotate around the center. So what we're looking at here is the dispersion of stellar velocities. If it's really fast near the center and it slows down out towards the edge, that's a big dispersion indicated by sigma. If it's pretty much the same rotation all through the whole thing, then it's probably not very massive and it's probably not all that bright. So that it would have a lower luminosity. If you can measure by the spectrum the dispersion of velocities near the center, take that to the fourth power. This is greatly oversimplified. That exponent has a range from 3 to 6, depending on what size of galaxy it is, but I decided to leave that out. Here's an average way that this works. Again, compare it to the visual magnitude and get the distance. And we can see that this actually has some error bars and some where they apparently thought the data should be down a little lower or something. But anyway, we got a fairly decent relationship here with the Faber-Jackson method. And it's, again, a tertiary method that leaves a lot to be desired. Here's one that's really neat, type 1A supernova method. First of all, what's a type 1A supernova? Well, they always occur in binary star systems, where one star evolved faster than the other because it was a little more massive, went through the red giant phase, sent out a planetary nebula, and now it's collapsed down to a white dwarf. Now the companion is just catching up by being a red giant. And they're close enough together where the red giant is letting its outer surface layers get sucked onto the surface of the white dwarf. And I guess we need to deviate for a moment about Chandrasekhar's limit. A white dwarf star can only have 1.4 solar masses maximum. If it's any more than that, it will collapse to be a neutron star. Subramanian Chandrasekhar was an extraordinarily bright Indian lad who won a scholarship from India to go to college in England, to Cambridge, no less. And he didn't have a lot of money, so he took the boat to England. And on his boat trip, on the way to college, he calculated what we now call the Chandrasekhar limit, that a white dwarf can only have 1.4 solar masses or less, or it will collapse under its own gravity. So what happens here is that this red dwarf dumps material on the surface of, or the red giant dumps material on the surface of the white dwarf until it gets right up to 1.4 solar masses, and then the next thimbleful causes it to collapse and explode as a type 1A supernova. Now the neat thing about that is they should all be the same brightness, shouldn't they? Because all stars are different size to start with, but when you get each one up to its tipping point at 1.4 solar masses and then it blows, the explosion ought to be the same regardless. And all the ones who've been accurately measured are, in fact, and they have an absolute magnitude of -19, as I recall. All of them, and that's brighter than the type 2 supernovae like the Crab Nebula. Those get to a maximum of -17.5, but this goes to -19 when the type 1A supernova blows. That means that if you can find one in some other galaxy, you automatically know what its absolute magnitude is, and then compare it to the visual magnitude and calculate the distance. Okay, so I've got another slide on that right at the end. Finally, the Hubble diagram, where we worked our way all the way to the top of the diagram here. Hubble has measured distances to galaxies, and spectroscopists had also measured the speeds of recession with the Doppler effect. And Hubble noticed that if you made a graph of velocity versus distance, you would get a very linear plot where the velocity was proportional to the distance. And this was early Hubble diagram, the velocity of recession versus the distance to the galaxies. That proportionality constant is now known as the Hubble constant. We can measure it from the slope of a Hubble diagram. Here's an example. The Virgo cluster of galaxies lies at a distance of 38 million light years and is receding 710 miles per second. If we do that calculation of the velocity divided by the distance, we see 18.7 miles per second per billion light years for the Hubble constant. The Hubble constant has certainly not been constant. It has been revised over the years. And I remember one time Dr. Bert Willett at Memphis State gave us a diagram showing the value of the Hubble constant versus the year. And it had a fairly linear relationship, which doesn't prove anything, but it was funny. Okay, we can also express it as kilometers per second per megaparsec. And the values have ranged from anywhere from 50 to 100 kilometers per second per megaparsec. And the best current values are around 71 to 75 for the Hubble constant. Now here's how we use the Hubble diagram to measure distances. Suppose we made a Hubble diagram with measured velocities and distances. And here's some more of the spectra that you were asking about earlier, how do we actually do that. Here's the spectrum of a quasar, 3C273. Here's a laboratory comparison that has hydrogen in the mixture. Here's the hydrogen beta, which is the electron falling from the 4th to the 2nd shell, and the gamma from the 5th to the 2nd, and delta from the 6th to the 2nd. Those are those lines. And in the spectrum of the quasar, they're moved way over towards the red end of the spectrum. They're not in the red, but they're red shifted by a tremendous amount. And if you go to calculate the speed from it, it turns out that that quasar is receding from us at 16% the speed of light. And we get that from measuring the spectrum of the object with a standard lab spectrum. Here's some other examples, and you can see kind of a small redshift there. This is a distance of 24 million parsecs, and we work our way on out through other galaxies to 1.2 billion parsecs, which is about 4 billion light years. And we see increasingly greater redshifts the farther away we go, indicating faster speeds of recession. Here's where I said, remember, this is our simple equation for way below the speed of light. We have to use a relativistic version when we get closer to the speed of light. And this, if you use this one when you should have been using this one, you'll get the same result. But if you use this one when you should have been getting this one, sometimes you'll get speed exceeding the speed of light, which doesn't make any sense. So this is the one that's more reliable that we have to use when it gets when we get some really rapid speeds like this. Here's one where all the wavelengths are doubled. 2,000 becomes 4,000, 5,000 becomes 10,000, and so on. So that would indicate that the thing is moving at exactly the speed of light. But if we use the relativistic equation, it only turns out to be 60% of the speed of light that it's receiving from us. So we have to make that correction out near the right-hand end of the Hubble diagram. Here's how we use it. Suppose we measure the velocity that it's receding. That's the easy part, isn't it? We just take the spectrum, see the line shifted, calculate with that equation. Measuring the distance is really hard. We can only do that accurately for ones that are close by. But if we measure the distance or the velocity of the very distant one, read over to the graph, and then, do I have the line on there? No, I didn't. Yeah, I do.
Yeah.
It's on there. Yeah, it's kind of faded out. We can read the distance off of this. Now, at this point in the evening, you know what's gone into all of these measurements and how much slop there is and how much wishful thinking and so on. So we don't know this within inches like we do the distance to the moon. But for things this far away, that's about all we are able to do. This is a really good one, isn't it? This is a nice line. This deals with type 1 supernovae. And that's the one where we make the assumption that all of them are the same brightness, minus 19th absolute magnitude. That gives us a very reliable line if we can find one of those in our distant galaxy. Now, if you can't see something that's magnitude minus 19, it's pretty much too far away to fool with. You'll have to wait for something else, because that is extremely brilliant.
I'm assuming the lines through the little circles was just slot?
Error bars, yeah.
Okay. And I would assume that the further up the line you get, the longer the line
Yes.
would get, but it doesn't always look like that's always the case. I mean, I see some of
It's
these.
pretty close to it. If you want to measure all these things, have at it, but in general, the farther away it is, the more uncertain we are on the distance. The spectroscopy part is pretty much constant. That's known
Okay.
almost exactly, but the distances, when you start putting in the plus and minus on the distance, it's a percentage of this. So the higher this is, the bigger that error bar is going to be. Okay, here's an example of that kind of calculation. You measure a galaxy that's receding from us at 9,500 miles per second, or 15.3 kilometers per second. How far away is it? And we're making this assumption that this is this year's version of the Hubble Constant, and we put that in and calculate the distance as 214 megaparsecs, or 698 million light years. So that's got about maybe too many significant figures. I'd call it like 700. Would be more reasonable than say we know that to that degree of accuracy, but this is the way the calculation just happened to come out. Okay, finally, why is this all happening? This is not on tonight's topic, but it's probably on your minds. Why does this relationship hold? And that's the most likely reason is because of the Big Bang. That if the whole universe started out at one point at some given instance in time and place, and expanded out from there, the most remote things are the ones that were moving the fastest. And the ones that are still lagging behind were not moving as fast, and that gives rise to the Hubble diagram. And we could spend 2 or 3 days just on that. But let's don't. That's okay. Does anybody have any questions for me?
I have one comment, and everything you said is correct. I would just say, in astronomy, if you don't know distances correctly, nothing else makes a lot of sense.
Yeah, many of those laws are just suppositions if you don't have something good to work with. But next month, if Tim will have me on, I will close the gap in between parallax and Cepheid variables. How's that? I gotta stay alive for another month.
Thank you.
Thanks, Bill.